So today we're going to start out by doing kind of a level set. We're going to cover some slides that you've seen before, just about the technology and the functionality that's available, because those are important considerations when you start looking at performance. Then we'll jump into some of the performance metrics that are available. IBM has published some white papers on what wonderful things the hardware can do. So we'll look at those because they can help you contrast some of the options available to you, things like AES versus DES encryption or secure key versus clear key versus protected key. Then we'll go into some operational factors, some parameters that you control in your ICSF options that can affect performance, and then some of the things that you can look at as you're trying to diagnose problems with performance and make sure that you're leveraging all of the infrastructure that you have available. And then finally, we'll come back and look at some of the performance data that's available. There are some reports, specifically an RMF Crypto Hardware Activity Report. We'll talk about what it can provide. So with that, let's go to slide 4. A reminder that the crypto hardware historically has been defined as either clear key or secure key hardware. With clear key hardware, your key material may exist in the clear somewhere in your environment, whether it's in a key repository or it's in memory when the application is using the key. Your key material will pass through memory. And if the key is in the clear, if somebody can look at that memory, they could possibly see the key. Secure key, on the other hand, provide some additional protection for your key material so that your key will not exist in the clear anywhere except inside the secure tamper-resistant boundary of the HSM, the hardware security module, that technology that provides tamper-resistant technology so that if somebody tries to tamper with the card, that would be recognized as an attack and the key material would be protected. Excuse me. We're going to see on the next two slides that clear key technology is implemented in the CPAC-F hardware, secure key technology is implemented on the Crypto Express card, and those two technologies have very different performance metrics. Protected key is the new kit. It's kind of a hybrid between clear key and secure key. With protected key, your key will begin life as a secure key. That is, it will be protected. The key material is encrypted under a master key when it's stored or used outside of the card. With protected key, your key will begin life as a secure key. It will then be decrypted under the master key, re-encrypted under another key called a wrapping key, and then that wrapped key can be used on the CPAC-F hardware. So the key material is encrypted, but that CPAC-F hardware, when it's used there, does not have that tamper-resistant, tamper-proof technology that's available to the Crypto Express card. So we'll see that each of those types of key material have very different performance metrics when we look at some of the white papers that are available. Let's go to slide 6. Again, the two types of hardware that are available on System Z are the CPAC-F, the CP Assist for cryptographic function, and the Crypto Express card. The CPAC-F has very limited functionality when compared to the Crypto Express card. That is, the CPAC-F can only do symmetric encryption. So it can do triple DES or AES encryption for all of the supported key links, and it can do SHA hashing, whether it be SHA-1 or now the SHA-2 algorithm. And the SHA-2 is actually a suite of algorithms with multiple links available for the hashing algorithm. But that's all the CPAC-F does, is symmetric encryption and hashing. And it's very fast. We'll see that in a minute, that those operations are very, very quick, but it's limited functionality. Let's go to slide 7. The other device that's available on System Z is the Crypto Express card. The Crypto Express card has significantly more functionality. It can do the same symmetric encryption that the CPAC-F can do. So it can do triple DES and AES encryption, but it's doing it with secure keys, so the key material is protected when it's not when it's outside the tamper-resistant boundary. So it does the same encryption, but because the Crypto Express card is installed in the I/O cage, it's almost an I/O operation to get work done. You have to send the work out to the card, let the card perform the operation, and then the results come back. So that's an asynchronous operation. If nothing else, you just have to, the application is going to have to wait for the work to be done outside in the card, and then the results return back. So the metric is going to be very different from clear key encryption. In addition, the Crypto Express card does the financial PIN functions. So the federal regulations require that PIN processing be done in an HSM, a hardware security module. So again, that work has to be sent out to the card in an asynchronous operation and the results sent back to the application. The Crypto Express card also provides a random number generator. So if you need a hardware random number generator, that's where the work is done. That's where your secure keys will be created inside that random number generator, inside the HSM, and the key material will be encrypted before the key material is sent back to the application and eventually stored in the key repository. The Crypto Express card also provides the support for SSL handshakes, which include RSA or elliptic curve encryption. Again, these algorithms are using longer key materials. In the case of RSA, now up to 4096-bit keys. It takes a while to perform that encryption, those RSA operations, and they're done on the card, again, an asynchronous operation. Keep in mind that the CPAC-F did not do anything with public-private key encryption. So all of those operations are done out on the Crypto Express card or possibly in software. We'll talk a little bit more about that in a minute. Protected key is enabled on the Crypto Express cards, so that beginning life as a secure key, that's where that happens, is on the Crypto Express card. And then finally, the Crypto Express card, the Crypto Express 4S supports PKCS 11, the public key standard that has been implemented and supported now on the zEC12. We're not going to spend a lot of time talking today about PKCS 11 support, but just be aware if you are using PKCS 11 secure key, that's going to be done on the Crypto Express card. Again, the I/O operation and waiting for the results to come back. Let's turn to slide 8. To kind of summarize things here, the other thing to keep in mind with the Crypto Express card is it can be configured in one of 3 modes. Again, the Crypto Express 4S will support enterprise PKCS 11 operations. If you configure the card in EP11 mode, that's all it can do. It will only do PKCS 11 operations. It can't do RSA operations using coprocessor mode or as an accelerator. It will not do the CCA secure key encryption. Now, PKCS 11 still supports secure key encryption, but it's strictly in the PKCS 11 mode. By default, the card is configured as a coprocessor. That is, it supports the CCA operations going way back to the PCI XCC, the Crypto Express 2 and 3 cards. Those type of operations are supported, and all of that functionality that we just talked about on the last slide is supported. So you can do secure key, triple DES, and AES encryption when configured as a coprocessor. You can support the financial PIN functions when configured as a coprocessor. You can generate keys, and you can perform RSA public and private key encryption and ECC public and private key encryption when configured as a coprocessor. Finally, you can configure the card as an accelerator. When you configure the card as an accelerator, it can only do public key RSA encryption on the accelerator. It's very, very fast, and we'll see that on a later slide, but that's all it can do. You can't do secure key AES or triple DES configured as an accelerator. So there's a performance point there when you're doing a lot of public key encryption. You would consider configuring the card as an accelerator to get that improved performance. And again, we'll talk about that a little bit more when we talk about the RSA operations, and then when we talk about some of the reporting capabilities that are available. Let's go to slide 9. So that's kind of the level set. The next several charts are really going to be talking about what you can expect performance-wise. Now, most of the charts that we're going to talk about here, most of the graphs that we're going to see, come from the crypto performance white papers that IBM publishes for the various KEX and the various hardware devices that are available. There's a reference at the end of the chart, so you can go look at these documents yourself. But just keep in mind that those performance documents were developed in an IBM test environment where they were trying to demonstrate the best performance available that you could get out of the technology. You should keep in mind that you're probably not going to be able to achieve that level of performance in your environment. Again, these were very blue sky, trying to highlight the wonderful capacities and capabilities of the hardware. When you actually start implementing applications that do lots of other things, your performance is going to vary. Your performance is probably not going to achieve these white paper numbers. But the white papers are valuable in that you can look at and compare technologies, compare the options that are available to you. So we're going to see that secure key encryption is slower, and you'll see how much slower. You need to factor that into your performance requirements as you develop an application. Now, all that said, this first chart actually comes from a tech doc that Ernie Noctegal published a couple years ago. He was trying to show the performance impact of software versus hardware encryption. So what he did was on a Z10, which was the current machine at the time, he had a 24 megabyte file that he encrypted using software encryption, software routines, routines that implement the DES algorithm using move character shift logical instructions. So they weren't using the CPAC-F or the Crypto Express card. And then he compared that to encrypting that same file on the CPAC-F and on the Crypto Express, or actually, I guess, a PCI XCC at the time. So that 24 megabyte file, he used a routine called BDK DES, which was supported on some of the older implementations of the CUSP and PCF software capabilities. Again, they used assembler instructions, multiplies, and shift logicals to implement the DES algorithm. With that routine, he was able to encrypt about 450,000 bytes per second. So that 24 megabyte file that he encrypted took almost a full CPU minute to encrypt the whole file, 56.82 CPU seconds. He then took that same file and using the native instructions on the CPAC-F, the KM instruction, he performed single DES encryption, and the bytes per second were just dramatically more throughput. He was able to encrypt about 597 million bytes per second on the hardware. And with triple DES, it dropped a little bit, but still 241 million was dramatically faster than the 447,000 bytes per second. Plus, not only did he get better throughput, but the CPU time was just ridiculously lower, 0.04 CPU seconds for single DES and 0.09, so less than a tenth of a CPU second to encrypt that 24 megabyte file using the hardware technology. So hardware is dramatically faster than software. Down at the bottom, he then encrypted the same file, but instead of using the CPAC-F, he used the PCI XCC card. Now, the bytes per second was actually slower. He didn't get as much throughput as with the software, but he still saves significant CPU because the total CPU utilization was 1.66 for single DES, 1.67 for triple DES. So a dramatic savings in his CPU cost to get the file encrypted using the secure key technology. So again, software encryption is significantly more expensive than hardware. If you've got to do a lot of encryption, you definitely want to use the hardware. That is just going to be much better than using software, much better performance and dramatic CPU savings to do the work on hardware. So let's go to slide 10. So on slide 10, first of all, this is adapted from the cryptographic performance white papers that are available. There's a reference there on the page to the ZEC12 white paper. And this chart actually gives us the opportunity to contrast a couple different things. But before we get there, notice that the y-axis is a logarithmic axis. That is, every line is a factor of 10. So the first thing that you're going to notice is that comparing clear key and secure key and protected key, performance is very, very different. For example, there on the top chart, with clear key technology, we were able to, or IBM was able to encrypt 50 times 10 to the 6th bytes per second with a 64 byte input block. So that was about 50 million bytes per second. Whereas with secure key, they were only able to do 0.148 times 10 to the sixth, or 148,000 bytes per second. So a dramatic difference there between clear key and secure key technology. Protected key, not quite as good as clear key, but still very much better than secure key technology. And if you look out to the right, as you go to a larger block size, you'll see that the protected key is almost as good as clear key out there with those larger block sizes. So the overhead of having to decrypt the secure key from under the master key and rewrap it under the wrapping key, the larger the block size, the less of an impact that has on each operation. Now, the other thing that these two charts compare is AES encryption versus triple DES encryption. So at the top we have AES encryption. We were able to do 50 times 10 to the 6 bytes per second with AES. With triple DES, it was only 47.7. But again, as you get out to the right with the larger block sizes, the performance difference is quite a bit more dramatic. AES encryption was able to do 1560 times 10 to the 6 bytes per second with a 1 meg input block, but triple DES was only able to get up to 385.8 bytes per second. So the other thing to note here is the impact of large blocks on your performance. If you have the choice of encrypting 1,000 bytes in one call, that's much better than encrypting 100 bytes at a time and doing 10 calls to encrypt the same 1,000 bytes. So if you have the option in your application to do some blocking and pass larger blocks, that is certainly preferable to using the smaller block sizes. So with that, let's go to slide 11. On slide 11, we're looking at SSL, specifically RSA performance, using software and then the Crypto Express cards. We saw this chart when we talked about System SSL a couple months ago, so we'll hit it kind of quick. But notice that with software encryption, in the benchmark runs, they were able to handle just over 1,300, almost 1,400 transactions per second in software. Now, this was running on a four-way ZEC12, and those almost 1,400 transactions per second consumed 100% of those four CPs. So we were using up a lot of horsepower to perform those RSA operations. When they introduced Crypto Express 4S's configured as coprocessors, the transaction rate went up significantly to just over 9,000 handshakes per second. And instead of using all four CPs, they were only using a little bit more than two of the CPs. So ICSF was having to do work on the general purpose engines to hand the work over to the Crypto Express cards, but the Crypto Express cards were doing the bulk of the work in terms of performing the RSA encryption and then handing the results back. And you can see that the four Crypto Express cards that were available were running at 100% to process those 9,000 transactions per second. When they reconfigured as accelerators, the throughput jumped, almost doubled again, up to 17,493 transactions per second. Again, ICSF was having to do a lot of work on the general purpose engines to hand that work over to the cards, and we were again consuming about 100% of those four accelerators. But the accelerators were doing a lot more work to get that throughput, to get those 17,000 transactions per second. So the hardware, the Crypto Express, whether you're talking coprocessor or accelerator, will give you better performance, better throughput, will give you some CPU savings to drive that workload. And then the accelerators will yet again provide even better performance if you can reconfigure as an accelerator. Let's go to slide 12. This slide is comparing performance across the generations. So it's looking at triple DES and AES clear key encryption, starting with the Z990, which only supported triple DES, those older machines could do about 120.4 times 10 to the 6 bytes per second of TDES encryption. The zEC12 today can do uh, 290 times 10 to the 6 bytes per second. So there's been a steady improvement in the triple DES algorithm. Similarly, the AES algorithm, which was support was introduced on the way back on the Z9, it could do 120.4, or I'm sorry, 179.6 times 10 to the 6 bytes per second. Today on the EC12, that is dramatically better, 644.3 times 10 to the 6 bytes per second. So this is kind of an advertisement that being on the most current technology will provide the best performance in the crypto hardware. Let's go to slide 13. And this is the same chart, but focusing on the secure key technology, the Crypto Express, and going way back, the PCI XCC cards. For AES encryption, AES secure key support was introduced on the Z10 GA3, and that first machine could do 9.54 times 10 to the 6 bytes per second. Performance is a little bit better today on the EC12. Triple DES, on the other hand, the performance improvement has been a little bit more dramatic, going way back to the Z890. You could do 2.7 times 10 to the 6. Now you can do 14.0 times 10 to the 6 bytes per second on the Crypto Express cards. So again, staying on current technology will provide the best performance. I will point out that this chart does look at 1 meg input blocks, whereas the previous chart for the CPAC-F hardware did 64 times 10 to the, or I'm sorry, 64 byte input blocks. So it is a little bit different metric, but whichever one you compare, the newer technology is going to give you the better performance. On slide 14, we see some similar information just for some other selected APIs. This one's looking at key generate, the clear pin generate, and encrypted pin verification. Again, later technology does provide better performance for those three APIs. The white papers that we're using here, there's a lot more information. There's a lot of other APIs covered as well. Now, it doesn't cover 100% of the APIs, but it covers many of the APIs that are available. If you are looking at implementing a specific API, it's worth taking a look at the performance white papers to see what the metrics look like for that selected API if they're available. And again, there's a reference at the end of the deck on the white papers that are available. Let's go to slide 15. So those charts provided just some comparisons of clear key versus secure key, AES versus triple DES. Again, you can go look and read those white papers and figure out the specific APIs that you're interested in. The next couple charts are going to talk about some of the configuration options that are available. We're going to start out with some of the ICSF options. We talked about these when we talked about ICSF, so we'll go through them kind of quick. Key auth and CKT auth are two options that have to do with providing key integrity. Going way back when ICSF was first implemented, one of the things that they did was when you create a key and when you save a key in the key repository, ICSF would calculate a hash of the actual key value and store that with the key in the repository. So when you came back sometime later, whether it be a day later or 6 months later, and wanted to use that key, ICSF could go calculate the hash of the key that it pulled out of the repository and compare that to the hash that was stored with the key. If they matched, ICSF knew that it had a valid key, that a bit hadn't been lost, and that the key was good. Way back on the old technology, that check was performed on the CCF hardware, and it was very, very fast. When IBM went to the CPAC-F and the Crypto Express hardware, those checks were now done on the Crypto Express card. out in the I/O cage, so there's an I/O operation to send the work out, wait for the results to come back. So there was a significant performance impact in continuing to perform those checks. So IBM gave you the option of disabling those checks. Key auth, the check is performed when you read the key from memory. So when ICSF starts, the data is read from DASD, and that's when the CKT auth is performed. When you pull that key out of the repository and put it in memory, ICSF would make the trip out to the I/O card and perform the check, make sure the key was good. With when your application actually used the key and you retrieved it out of memory, ICSF would also perform that check and make sure it was still good. Given the technology today, the integrity of the hardware technology, IBM really doesn't feel like you need to continue to perform those checks. The hardware is good enough. It's going to protect and provide the integrity for your key material. So for some time, they've been recommending that you set key auth and CKT auth to no and not perform those checks. And in fact, with the latest version of ICSF, HCR 77able1, those checks have been deprecated and they are not even supported anymore. So IBM recommends that you set those to no and just skip those checks altogether. Checkauth, on the other hand, is a little bit different. Checkauth tells ICSF if your calling application or your calling program is running in supervisor state or system key, you can tell ICSF, don't even bother performing the SAF check to see if that caller is authorized to use the particular key or the particular API. And the thinking here is that if you are letting the code run in supervisor state or system key, that implies that you trust it, that you've done some due diligence, made sure that the application is doing what it's supposed to be doing and not using APIs or keys it's not supposed to be using. So by skipping the SAF check to see if it's authorized, there's some performance benefit there. Now, if you've done the due diligence, if you trust the codes that are making the crypto calls, it makes sense to set checkauth to no and not perform those SAF checks. If you don't trust it, then maybe you need to leave this as checkauth yes and continue to perform those SAF checks. And then the other ICSF option are the sysplex sharing capabilities. If you are sharing a key store between multiple LPARs, you need and must specify sysplex CKDS, PKDS, TKDS yes to tell it you are sharing, and in that case, ICSF will manage the NQs and any of the contention between the LPARs in accessing those key repositories. The documentation doesn't really come out and say it, but if you're sharing them, you must specify yes. Starting with HCR 7790 and then fully implemented in 77able0, ICSF sysplex sharing was completely rewritten, is much more efficient. You will get much better performance if you're running on those later versions of ICSF when you're sharing the key stores. Then finally, there are two new security policies that are available which give you the ability to disable the SAF checks for the one-way hash and the random number generator. Now, with the one-way hash, what happened here is the one-way hash, you could perform the way back, the CCF operation, the one-way hash was done on the CCF. It was only available via an API. When IBM implemented the CPAC-F hardware, that one-way hash was now supported by an assembler instruction on the CPAC-F hardware. There is no way to restrict access to a specific assembler instruction. So anyone can perform a one-way hash by invoking the KIMD or the KLMD instruction and performing the hash. There was still the API, the SAF check for the API, though. So if somebody was calling ICSF and telling it to use the instructions to perform the hash, there was still that SAF check going on. Well, it doesn't really make sense to perform that SAF check if somebody can get around it by just calling the assembler instruction directly. So with the latest version of ICSF, you can tell ICSF, don't even bother checking the SAF call for the API for the one-way hash. there's no point in it because people can get around it anyway. You could set the one-way hash and give it a UACA read and give everybody access, but you're still performing the SAF check, and that has an impact on your performance. But so by setting this policy to disable, you're just telling ICSF, hey, don't worry about it. People can get around it. Just skip that SAF check. The random number generator, that policy is a little bit different. The random number generator was implemented on the Crypto Express card, and theoretically, it was possible to have a denial of service attack by making thousands or millions of calls to the random number generator. And every one of those would require a trip out to the IO cage to the Crypto Express card. If you got enough of them, you could bottle up the Crypto Express card. With HCR 7780, IBM changed the way the random number generator works. And what they do now is they provide a cache of random numbers. So as soon as ICSF comes up, it will start making calls to the Crypto Express card, creating random numbers, and then putting those into a cache. When you actually execute the API, instead of going out to the card and waiting for the results to come back, ICSF will service the call from the cache. So that issue of a denial of service attack is no longer valid. The cache is going to keep up with and provide the data much more efficiently. So once again, you can tell there's no point in protecting and restricting who can do a random number generate call. So you now have the capability to say, just disable that check. Don't go through the overhead of a SAF call just to check and see if they're authorized. Just give it to them out of the cache and let's keep things moving. So those might help you if you're doing a lot of one-way hashes or a lot of random number generates, just the savings on the SAF call to see if people are authorized. Let's go to slide 16. If you're trying to look at, if you think you have a performance problem with the crypto hardware, the next couple slides are some things that you can look at to make sure you are taking advantage of your hardware. The first thing to check is to make sure that the microcode that enables the crypto hardware is installed, feature code 3863. If you go to the HMC and get into single object mode and look at the CPC details, down in the bottom right, you can see CP Assist for cryptographic functions installed. That says the microcode is installed and you can use the CPAC-F and the Crypto Express cards. If it says not installed, that means you don't have the microcode. You need to go back to IBM and get that no cost enabling code. Let's go to slide 17. Now, assuming you're authorized to use this crypto hardware, the next thing to check is to make sure that you have Crypto Express cards installed. If you're expecting them to be there, you need to check this slide from the HMC as well. Go to the CPC operational customization and then view the LPAR cryptographic controls. On this slide, we can see that we have 5 Crypto Express cards installed. They're all Crypto Express 4Ss. The cards in slot 0 and 6 are configured as coprocessors. The cards in slot 1 and 2 are accelerators, and the card in slot 7 is in EP11 mode. So this tells us that the KEC has access to Crypto Express cards. So that would probably be the next thing to check. Then you've got to make sure that these cards are available to the particular LPARs that you expect them to be available to. We can see that on slide 18. This is the LPAR activation profile. This particular LPAR has been assigned the cards in slot 6 and 7. That online list there on the far right says that if there's a card in slot 6 and 7, it will be brought online when this LPAR is activated. If the candidate list is checked, that card is eligible to be brought online sometime later or after the LPAR is up. In this case, we don't have any assigned in the candidate list, but if we did, let's say that card crypto number 1 was checked, we could add a card sometime later into this KEC And by virtue of it being in the candidate list, that card could be brought online to the LPAR at some point later. So you need to make sure that not only do you have the cards available, but are they properly assigned to the LPARs and available to the LPARs. Then on slide 19, the next check would be to make sure that the master keys are loaded so that you can use the card. For the coprocessors, you must have a master key loaded to be able to use the coprocessor. This is the coprocessor management screen from ICSF. You can go look at the panels, and the status column of active tells us that that card is active and available to be used in that LPAR. So one of the first things you're looking for is the status of active. You're also going to look at the master keys that are installed and make sure that the master keys that you need are available. Now on this slide, the DES master key is uninitialized on all of the coprocessors. That is, there's been no DES master key loaded on any of the coprocessors. If you're not expecting to use DES on this LPAR, that's perfectly reasonable, perfectly acceptable. You can still do AES encryption and you can still do ECC on this LPAR, but you cannot do DES encryption. If you were expecting to use DES or triple DES, then this would be an indication that you have a problem. The master keys haven't been loaded. You're not able to use those coprocessors right now for DES encryption. So this would be another check you would perform, just working your way down to see what's available to the KEC, what's available to the LPAR, and okay, it's available to the LPAR. Do I have it fully initialized and ready to use? Let's go to slide 20. Another thing you can look at is specifically if you're looking at SSL performance is you can ask System SSL what it thinks it has available in terms of hardware and software support. There is an SSL start at task that you can start, and then once you do, you can query that start at task to say what crypto support is available. And on this slide, we can see that RSA encryption for encrypting and signing does have hardware support up to 4096-bit keys. So that tells us that there's a Crypto Express card, a coprocessor accelerator available to the LPAR, and that's where those 4096-bit keys are going to get routed. Now, if you were expecting ECC support on that Crypto Express 4S, the fact that there's a dash down there under hardware says there's something wrong. He doesn't see it. So on this system, either the master keys weren't loaded, or we didn't have Crypto Express cards that supported ECC on this LPAR. So you can query SSL, and he'll tell you when he's got hardware support. Let's go to slide 21. We haven't talked about the CPU measurement facility before. The CPU measurement facility was implemented or made available starting with the Z10s, and what the measurement facility is a capability for counting instructions. It was used internally within IBM for testing and measuring things, and then starting with the Z10, it was made available to customers as well. And what it does is it gives you the ability to count individual and similar instructions, including the crypto instructions. So the KM and the KMC instruction, which does DES encryption and pseudo-random number generator, there are counters there for how many times you perform a pseudo-random number generate or a DES encryption or an AES encryption. And then the KIMD and the KLMD instruction implement SHA hashing. There's a counter there for SHA as well. There's a function count and a cycle count. The function count is how many times the instruction was called. The cycle count is how many cycles they used. Notice there's also a blocked function in cycle count. If you remember when we talked about the CPAC-F hardware, on the Z9 and the Z10, there was a 2-to-1 relationship of CP to CPAC-F. So each CP shared a CPAC-F. If CP0 was using the assembler instructions on the CPAC-F, CP1 could not get to that CPAC-F. And in those cases, you'd see a blocked function count. Now with the Z196 and the ZEC12, we've gone back to a 1-to-1 relationship, and you should never see a blocked function count or a blocked cycle count for those machines. But basically what the measurement facility is doing is just a counter of instructions. Let's go to slide 22. John Berg, who's one of the performance people in the Washington System Center, has done some analysis of the CPU measurement facility, done some counts. What those counts can do, what those function counts and cycle counts can do, is give you an estimate of how much of your general purpose engine is being consumed by crypto. So he ran a test at the Washington System Center where he did some DASD. He was dumping DASD and encrypting the dumps as he created them. And when he was doing that, he was running multiple in parallel, but it was only using about 2.5% of the general purpose engine. John has developed some tools. He can help you do some of that analysis. Again, at the end of the deck, there will be a reference to some of his material, and you can contact him for help in analyzing the results. Let's go to slide 23. Shift gears a little bit. Talk about the SMF data that's available. The Type 82 record is generated by ICSF. You'll notice that some of these are grayed out. The grayed out items are associated with the CCF hardware, which is very old. Starting with HCR 77ABLE1, IBM dropped support for the CCF hardware, so these are no longer available. If you're running on old CCF hardware with an older version of ICSF, you might see some of those grayed out entries. The ones that are in black, as we go through these, you're going to see that the vast majority are event records. They are created when something happens. For example, when ICSF is initialized, or for subtype 7, when you load a key part into the master key registers, there's a record cut saying that this happened. Let's go to slide 24. Here we have several more event type records. The dynamic PKDS update. When the PKDS is updated, subtype 13 is going to get cut. So subtype 14 will get cut when you load a master key into the crypto coprocessor. But notice down at the bottom, subtype 19, PCIX cryptographic coprocessor timing, and on slide 25, the subtype 20 at the top, those two records do provide some performance data, but they are really just sampling some of the cues of what's going on in the hardware. So you can't really use those to evaluate your performance or predict your capacity requirements. There are a number of other subtypes on this chart that are, again, event records of when things happen. So be aware that that data is available. And then let's go to slide 26. There's also a RexExec and a sample job provided for printing those records, those Type 82 records. The SMF job will run IFA SMF dump to extract the Type 82s, and then it does a sort by date and timestamp. And then finally, it executes a RexExec that will print some meaningful data from the SMF Type 82. So for example, there we did a subtype 14, which was that coprocessor timing. We can see things like this was from system ID sysc. It's got the date and timestamp, and there's a little summary that, okay, the Type 14 is written periodically to provide some indication of coprocessor and accelerator. If you really want to understand a lot more about what's going on, you're going to have to go to the Systems Programmer's Guide and look at what those bits and bytes mean in terms of what was going on at the time. So because most of these records are event records, this is more of a forensics report. It's not really a performance report. You wouldn't use the Type 82 to do performance analysis. Let's go to slide 29. There is performance data generated by RMF, specifically the Type 70 subtype 2, which is the RMF processor activity report. This does give you some performance information. There's 4 sections in this record. There's the coprocessor data section, the accelerator data section, and for each of those, there's a little bit of detail about what's going on. Let's go to slide 28. There's also a PKCS 11 section now, so if you have cards configured in EP11 mode, there will be a section for each of those cards. And then on slide 29, there's also an ICSF services data section, which has some detail about actual calls to the APIs. So the type 70 record is cut by RMF. It does have some crypto data in it, and that data is uh, reported on in an RMF crypto hardware activity report. Let's go to slide 30. So this is the report that's generated from those type 70 records. So again, there's going to be 4 sections in this report. There's the coprocessor, there's a PKCS 11 coprocessor section. On the next slide, we're going to see there's an accelerator section and an ICSF services data section. So let me point out a couple things here. First of all, this report comes from an RMF manual. I don't think this is a valid report. We see there that there's a Crypto Express 2 coprocessor, a Crypto Express 3, and a Crypto Express 4. There isn't any KEC that supports all of those coprocessors to be installed at the same time. So this report is just kind of a sample that they generated. But what we can see here is that the coprocessor in slot 1, which is Crypto Express 2, was being used at almost 64%. The Crypto Express 3 was running at 48.9%. Now, the first thing you have to keep in mind is that this report is for the entire card. So if you remember, each of the coprocessors can be assigned to up to 16 different LPARs. So we might have that second card there that's running at 64%. That work may be coming from one LPAR that is using 64% of the card. Or there might, if it's assigned to 16 LPARs, each one of those LPARs might be running at 4% utilization to give you the 64%. So it's kind of hard to tell where the workload is coming from. You also can't tell what applications are calling the card. So this data isn't really useful for performance metrics. You can't do, or especially can't do capacity planning from this chart. The best you can do is probably monitor these numbers, look at the RMF hardware activity report every day and start trending the utilization on the cards. And as your utilization gets higher, then you have to maybe look at adding other cards into the mix. For the coprocessor section at the bottom, you got the same thing there. You've got a utilization number of 11%. If you go over to the right, the operations details, you'll see that 11% consists of 3.1% asymmetric fast operations, 6.5% asymmetric slow, and 1.4% symmetric partial. Now, the RMF manuals don't really define what asymmetric fast is versus asymmetric slow. So it's really hard to tell exactly, what operations, what APIs are in the mix here. So if you have application X that is doing a certain amount of work, PKCS 11 work, and you know that you've got you're going to be expanding that workload and maybe doubling it, you're projecting the workload's going to be doubling it, it's kind of hard to predict what the impact is going to be on your utilization because you don't have enough detail out of this coprocessor section. Let's go to slide 31. We got a similar issue with the accelerator section. Now, the accelerator does tell you by key length type how much work is going on. So the bulk of the work on this system was 1024-bit RSA keys. They were using 18.9% of the card in slot 3 and 13.2% in slot 5. It's unfortunate that that coprocessor section on the previous page, the coprocessor can do these same operations, but we don't have a similar breakdown by key length for the coprocessor section. If we did, that would give you some clues in terms of when you would need to consider reconfiguring a card from coprocessor to accelerator, or vice versa, maybe reconfiguring an accelerator as a coprocessor. I spent a lot of time in the last couple years kind of arguing with development that they needed to provide more detail for the coprocessor in terms of these RSA operations, as well as just a lot more detail in general about the performance metrics that are available. And I think they've agreed and they understand that they do need to provide better, but there's a couple issues. First, those metrics have to be engineered into the hardware. So the hardware has to surface that information back to RMF and ICSF. Second, there's an issue of if you provide too much performance metrics or too much detail, that might enable some what are called side channel attacks. For example, if an attacker knows that a Crypto Express card is only being used to do triple DES encryption, then that helps them narrow their attacks that they might make on the card because they don't have to worry about is it RSA work that we need to analyze or is it AES work. If they know it's a particular type, it does make an attack a little bit easier. So there's a trade-off there, and I think IBM is going to provide better metrics, but it's going to take a while before it to be surfaced. And then the last section there is the ICSF services sections. That's some of the counters in terms of AES, triple DES, encrypt and decrypt operation, the number of MAC calls, the number of hashes that were performed. So there is some data available, but really what you have to do is look at the performance trends over time and kind of monitor these numbers over time, develop some familiarity with your environment and the particular work that you're doing in your shop. Let's go to slide 32. Also be aware that starting with the EC12, the system activity display, there was a new screen that was enabled to give you a snapshot of the crypto coprocessor utilization. This is the same number that showed up on that the RMF report, but this is just a snapshot. So you can take a quick look. If you see that all your crypto cards are pegged, that might be an indication that there's a bottleneck or something going on and tying up those cards. On slide 33, there are some other crypto fields in some of the RMF data, specifically the workload activity report. The type 72 subtype 3 has some sample numbers, so it will go in periodically and look at the length of queues and give you some information back about the length of the queues. If you see in your workload activity report an application is being delayed for crypto reasons, that's an indication you need to do some analysis. Maybe adding a card might solve the problem, but at least if you see delays, know that you need to do some analysis and try and figure out what's causing those delays. On slide 34, there's the SMF type 30 is the common address space work record. There are some ICSF service counts. There's counts of the number of calls, the number of bytes, and the number of commands that were processed for a couple different APIs. Not all of the APIs, but some of the APIs that are available. On slide 35, be aware that Omegamon does have some reporting capability. Now, this screenshot is from an older version of Omegamon. I presume it still supports it. What Omegamon did was they used the exits, the API exits that were available. If you remember when we talked about ICSF, many of the APIs support an exit capability, and what Omegamon did was they install an exit that basically just increments a counter every time the API is called. So Omegamon can generate a snapshot of what's going on in terms of the various APIs, a count of how many were being called. Now, my understanding is Omegamon is a real-time monitor. It doesn't create an archive or a history file that you can go back and post-process. You'd only be able to look at the real time. But if you've got Omegamon, that might be something worth checking periodically just to see what normal is in your environment. So on slide 36, kind of wrapping things up, there is some performance data available. It's a little bit hard to interpret, but I think IBM is going to get better in terms of the performance data and the capacity planning data that they provide. Looking back at the white papers or the graphs that we looked at, your application is probably the most significant thing in terms of what you can expect performance-wise. If you implement secure key, it's going to have higher performance requirements than if you implement ClearKey. And if you can, you want to code those applications to throw large blocks of data to the crypto hardware, not small blocks. There are some ICSF options that you can tweak to maybe squeeze a little bit better performance out of your system. And my basic recommendation is start generating these reports. Do the RMF crypto hardware activity report now. Start generating those counts and start developing trend lines so that as you see your workloads go up, you can understand what's going on. The last couple charts are the reference material. The last two on there are red papers. The effective or the monitoring system Z cryptographic services there at the bottom is a red paper that's focused on crypto performance. The one above it, the effective Z series performance, that has a chapter on crypto performance. Those are kind of old, but they are still very applicable. They don't cover PKCS 11, but they're still very applicable for the CCA support. On slide 38, the white papers that those graphs came from. So if you're running an EC12, you'd look at the first one. If you're running a Z196 or Z10, you could see similar data for those machines. ComServer, every version of ZOS, the ComServer folks present some performance data related to ComServer. Since ComServer can use the crypto hardware, especially for RSA, for SSL, and TLS, there are some things in those reports related to crypto. You have to go through and pull those out, but there is some occasional performance data for crypto in there as well. And then lastly, John Berg's white papers and red papers and share presentations for the CPU measurement facility. They can give you some help in getting that CPU measurement facility enabled and starting to collect data about the crypto work that's performed on the CPAC-F hardware. So with that, on slide 40, I'm going to turn things back over to Jerry and let him open it up for questions.